In this topic, we are going to talk about distributed NoSQL databases. We spoke in the first section when we talked about NoSQL databases about some of the characteristics that a NoSQL or non-relational database might have. And a couple of the things we said there were that NoSQL databases were designed to run well on clusters, to work well on the 21st century web, so where we have web applications and so on, and where we have large amounts of data as well. So in this topic, we're going to talk about a few of the ways that this is achieved using Mongo specifically. So first we'll just talk about how we can scale or grow our database and the two different approaches we can take with that. We'll talk about clusters and sharded clusters, which are specific to MongoDB, also replica sets, and then consistency in distributed systems and the CAP theorem. I suppose those last two are not specific to Mongo, but just kind of general concepts around that. So first of all, how we can grow a database. So when our database does start to grow bigger, or our needs, I suppose, for the database start to grow bigger, there's two different ways we can deal with that. The first, vertical scaling, would probably have been maybe the more traditional approach in the past with relational databases, is that when your database needs to get bigger, you increase the size of the instance. So you increase the size of your database server, the RAM, the CPU, and all the rest. You need to have, bigger servers that can store more and process more and so on. The other approach is horizontal scaling, so adding more instances. So you kind of keep a very similar sized machine to store the data in terms of both the storage capacity and again the processing power and so on as well, but add more of those different servers. So you're going to kind of spread the load, the increased load, over a number of different servers or clusters. So MongoDB it uses clusters and it supports horizontal scaling by using sharded clusters, which we'll talk about in a second. One of the benefits of using clusters and again the horizontal scaling approach as opposed to vertical scaling is the cost involved. So with vertical scaling, we probably be looking at increasingly more expensive hardware and so on, whereas with horizontal scaling we can keep using relatively cheap servers and so on, but just add more of them. Okay, so we'll talk about clusters and sharding in MongoDB now, and also replica sets, which they use to provide fault tolerance. And just to say the term cluster in relation to MongoDB, this is what they call a cloud-based MongoDB deployment. So we've just done a local MongoDB deployment so far, but once you're talking about a cloud-based deployment, then it's referred to as a cluster instead. MongoDB have a tool called Atlas. That's their cloud-based hosting service for deploying MongoDB websites in the cloud. Okay, so when we do have our database hosted in the cloud on a cluster in MongoDB, sharding is one of the methods that we can use to distribute data across multiple machines. So sharding here, you can think of as, something that's broken into a number of different shards, is their term for it. So in this example here, you can see this particular data is split into two shards, but obviously it can be however many is needed. Then we'd have one or more routers. The routers would manage data requests coming from whatever applications, and route them to the shards where that data is held. And there's also configuration servers involved in terms of using replication, which we'll talk about in a second. Okay, so this is the overall structure of it. And an example then, it might look something like this. Okay, so we can split collections over a number of different shards, like you can see here. So this collection 1, is split between 2 different shards, the shard A and shard B. You don't have to have all of your collections split though. So collection 2, as you can see here, is just held in shard A. We can imagine maybe, let's say this is a company that has a headquarters in Dublin and then another warehouse or something like that in Waterford. So you can imagine here, if we've got a warehouse, the warehouse documents for Dublin would be stored here in shard A, the Dublin shard. Maybe the Waterford warehouse documents would be stored here in close, in the Waterford shard or cluster. And then maybe because this operation here is the headquarters, this collection could contain, information about employees or payroll or whatever other stuff you might find at the headquarters of a company. Okay, you can see then here how the Mongo router manages requests. So from our applications that are using Mongo, we might have a number of read and write requests coming in. The blue ones represent this collection. So the router will route the request to the appropriate place. If it's a request to do something with one of the Dublin documents, it'll route it to here. If it's for the Waterford documents, it'll route it to here. And any requests on this red collection will obviously go to this cluster. Okay, so that's an overview of how that works. An example then, if we do have a setup something like this, so we're hosting a database in 3 sharded clusters and each site hosts its own orders data. So for example, Munster, Connacht and Leinster, we have maybe one warehouse per province, and all the information about that sector is stored there. So all the orders from Munster in Munster and so on. What can go wrong with this is if one of the sites go down. So that would mean, I suppose, at this time, while this site is down, the Connacht site won't be able to do anything with their orders, which you might expect. But it also means that the Munster site can't access the Connacht orders, and the same for Leinster. So it means that basically all those orders are down for everybody across the whole, like nationwide, while the connection is down. So those orders will be unavailable. So another thing that Mongo does, like I said, to provide fault tolerance is replication. So replication is essentially keeping a second copy, or maybe more than a second. You could have a third and fourth and so on, but multiple copies of data in a different location. So it provides redundancy, meaning there's always more than one copy of any given piece of information, and therefore that increases the availability of the data. If one site goes down, the data can be accessed somewhere else instead. Okay, so it's provides a level of fault tolerance against the loss of a single database server. In MongoDB, the terminology for this is replica set. So a replica set is a group of server processes that maintain the same overall data set. So in our example, to go back to that, this is the setup that MongoDB recommend for replica sets or replication. That it would be something like this, that at the Munster site, would be the primary holder of all the orders that are to do with Munster, and then they would maintain maybe the Connacht orders as well, and this is a secondary copy of the Connacht orders here. And you can see that in Connacht, this site is primarily responsible for these orders, and it also stores the Leinster orders and so on. So every site is kind of still responsible for their own data primarily, but also has a backup copy of the data from another site. So if any one of these goes down, the information will be available in another site. If they both go down, if 2 go down, then we have a problem. But in practice, we might have a few different copies, more than just two. But this, yeah, hopefully you get the idea from this anyway. How the replication itself works then. So the writes are generally made at the primary site and then propagated to secondary sites. So we saw earlier the router, which is routing writes and reads to different sites. So if I'm doing a write operation on, let's say, the Munster orders, it's going to route me to the Munster site to do that to do that write operation. Then they're propagated to secondary sites. So as you can see here, reads and writes usually go into the primary site and then being replicated to secondary sites. The way that this is done, or the timing, I suppose, of how this is done, it depends on your setup. I'm going to talk about that a little bit more in a while, but it depends on the application, I suppose. If it's something where it's really important that all of the sites have exactly the same information all the time, then you probably need to do something like locking the information at the secondary sites. That basically that the update is done almost immediately on the primary and the secondary sites. MongoDB by default, it does do the replication straight away, so there's probably a very short delay of a few seconds maybe that the information is maybe different if a write is done at the primary site and the time it takes then for that to get to the secondary site. Okay. So that actually brings me on to the next topic, talking about consistency in a distributed system. So like the example we've just seen, there can be issues where some nodes haven't yet received the updates while others have. So just to go back to this, if we do an update on the primary site, it's going to get replicated eventually to the secondary site. But even if things are working correctly, that'll take, a second or two. And if the link between this primary site and this secondary site goes down, then it might be a longer amount of time until the update is reflected there. So that might mean that we have information that's inconsistent between the different sites. Again, the priorities of your system we'll talk a little bit more about in a while. Sometimes you want to make sure it's always consistent. Sometimes you're okay with what they call eventual consistency. So that means that once an update is done at the primary site, it will eventually be reflected at all the different sites, even if it's not straight away. To get good consistency, you need to involve many nodes in data operations, but this would increase the amount of delay. So like I said there, if we want to make sure, say if it's a financial application, then it's really important that all the sites have up-to-date information all the time. Then what we would need to do is make sure that as the update is happening here, it happens here and here at the same time. So basically that all three get updated at the same time. And if the link is down between any of them, then that means we can't really do that update because it won't be done at the same time for all three. So that might mean there's a delay, we can't do certain things while a network link is down, and so on. So like I said, it depends on your application whether you want to prioritize consistency always or minimize delays. And it's a bit of a trade-off between the two. And the theorem then that describes what we've just talked about there is the CAP theorem. So this states that it's not possible for any distributed system to provide all three of these guarantees: consistency, availability, and partition tolerance. Partition tolerance means if a network link goes down between two sites, does the system overall kind of tolerate that? And the idea here is that you can either if you're tolerant of partitions, then you can only provide consistency or availability, but not both. And we'll look at a few examples now of what that actually kind of means in practice. So here, this example where Anne is trying to book a room at a hotel in New York, and she's booking it on a system node that's located in London. Ramesh is trying to do the same, and he's located on a node in Mumbai. And there's only one room available, and the link between the two breaks down. Okay, so what is going to happen in the different systems, I suppose, where the priorities are different. So, for example, if we want to provide consistency over availability, what will happen in those different scenarios? Okay, so first of all, I suppose a system that is trying to be consistent and available, it can't be all three. So that means this system isn't partition tolerant. In the event of a loss of network access, then that means we actually can't do anything. So that's how that one would work. In a system where we're trying to prioritize availability and partition tolerance, that means when our network partition happens, when the link goes down, that we're going to prioritize availability. So we want all our sites to be able to continue their read and write operations even when the network link goes down. So in that case, that system would accept the reservation in both sites. Even though there's only one room, obviously that leads then to an overbooking, and you have to resolve that problem some other kind of manual way. I don't know how, but maybe cancel one of them and whatever. But that's what would happen in a system that's prioritizing availability. A system then that prioritizes consistency in the case of a partition is in a system like that, one site would be designated as the primary node for the booking system. So in this case, let's imagine it's the Mumbai node. That means that node now has priorities to do write operations. So Ramesh would be able to go ahead and make the reservation. Anne would be still seeing the information that there's a room free, even though, in the meantime, Ramesh has booked, so it's not actually accurate information anymore. But because the London node isn't able to write to the system, she wouldn't be able to make the booking. So there still can be issues with out-of-date information appearing to people at other sites, but at least we don't have the same issues with consistency. Okay. So hopefully that example kind of explains what would happen in those different scenarios. To come back then to MongoDB and where does that fall in with the CAP theorem? Like this diagram shows here, you can basically pick two of these. So the systems that kind of tend to provide consistency and availability are relational systems like MySQL, and a few others here as well. Availability and partition tolerance are these ones here, and consistency and partition tolerance are these ones here. And you can see MongoDB is one of those. Okay, so it's strongly consistent. It prioritizes replicating updates as fast as it can, but in some cases availability can be prioritized and it goes for eventual consistency instead of immediate consistency. So that depends on your settings for your replica set in MongoDB.